So welcome back to this particular lecture where we will discuss about the star and the delta connections. So let's consider here the connection of a three-phase generator, how it is connected to the load is shown here. So this is in previous video we have seen what is a single phase and what is a three-phase system. So in single phase we will be having only one phase wire and neutral wire, and in three-phase system we have three phase wires, say R, Y and B. If it is a three-phase system, then we have three phase wires. This is three-phase three-wire system, and if we have three-phase four-wire system, then we have three phase wires and one neutral wire. So these we have already seen in the previous video. So let's say here this entire thing, it forms a three-phase network. This is my one single phase. This entire loop, it is one single phase. This entire loop, this is my another single phase. This entire loop, it is another single phase. Okay, so this is altogether a three-phase network. Okay, and this R is acting as the load, and these connections, these are my generator side or at the source side. Okay, now we can see for each phase system, if we consider for this one, so for this phase you can see the current IA is flowing from the generator side and it is going through the load, then it is again returning back through this path. Okay, if you look at this single phase system carefully, then the current IB is flowing from this phase wire, then it is going to this load, and through load it is again returning back. Okay, if you consider this bigger single phase system, the current IC, it is flowing from this phase and then it is passing through this load and then it is again returning back. Okay, now we have three return paths for each of these single phase network. So why don't we connect, or why don't we make a common connection of this return path? That means instead of these three conductors which are presently used as neutral paths, why can't we make them a single path? Because if you look at this system, we have total 6 conductors, 1, 2, 3, 4, 5, 6. But if we make all these neutral or return path a single path, then the number of conductors we can actually reduce from 6 to 4. Here instead of 3, we can use a common return path for all these individual single phase systems, right? So this common path is for all the currents IA, IB and IC. Okay, so what is the advantage? Now the number of conductors has been reduced from 6 to 4. So that leads to a great cost saving, right? Now the current that is flowing through this common return path, that is called the neutral conductor. Okay, and all these phase currents, all these this is a generator side and this is my load side. So each of these phase, they are in, this is a three phase system, so each of these phase, they have 120-degree phase difference from each other. That means they are 120-degree out of phase with each other. Now let's say this red color waveform is represented by this current IC. This black color waveform is represented by current IA, and this blue color waveform is represented by this current IB. Now each of these currents, they are 120-degree out of phase with each other. Now if we take if I want to find out what is the total current that is flowing through these common return path or neutral conductor at any instant of time, what will happen? Let's see. If see here, x-axis is my phase and y-axis is my magnitude. Okay, so at any instant of time, if I want the summation of all these phase currents IA, IB and IC, then what will happen? IA, IB and IC, what will happen? Let's say I'm considering this instant 240 degree. At this 240 degree instant, this current, red color waveform, it is maximum, it is 1. And the blue and these black color waveform, they are as at minus 0.5. So if we add those 1 minus 0.5 minus 0.5, then we are ultimately getting 0. Similarly, if we take at any instant of time and do the summation of all these three currents that are 120 degree out of phase with each other through these common return path, we will get 0. That means what? That means we can remove this common neutral path also. In that case, we can achieve 50% cost saving, because now my number of conductors has reduced from 6 to 3. Now only 3 conductors are there, right? So number of conductors has reduced 6 to 3. The cost saving is 50%. Okay, but we could remove this neutral conductor, since the sum of all the currents through this neutral conductor is 0, and that is only possible when we are having the balanced load or equal load. Okay, then only we can remove the neutral conductor. But if we have unequal loads, then what will happen? Then it will cause unequal voltage drop across each load, and in that case we have to include the neutral conductor. Otherwise, if we have the balanced or equal loads, then since the current flowing through that neutral conductor is 0, we can easily eliminate the neutral conductor from our circuit, and it won't affect my voltage and current in the network, and in this way we can actually reduce the cost of the conductor. Next, so this is my generator side, as I told. So this is a 3-phase network. If you carefully observe this network, it looks like a star connection. It looks like the Greek letter Y or the star connection. Okay, so, and this is the common neutral point. Okay, so in this case, this is a 3-phase 4-wire system. 3-phase 4-wire system. We have 4 wires and 3-phase 4-wire system. Okay, now the voltage, the potential difference between these line A and these point N, it is called the line to neutral voltage or phase voltage. Okay, and the potential difference between these line A and these line B is called the line to line voltage. So the potential difference between two line is called the line to line voltage, and the potential difference between a line and the neutral point is called the line to neutral voltage or the phase voltage. Okay, now let's say you consider this network. This is also a star network or Y network. Okay, so this is a 3-phase system. So here, let's say this is my VNR, this is my VNB, and this is my VNY. What does this mean? These are my line to neutral voltage. VNR is my line to neutral voltage. That means the potential difference between these line R and these neutral point. This is the line to neutral voltage or the phase voltage. This is VNB, means what? This is the potential difference between this line B and this neutral point N. VNB, that is the line to neutral voltage or the phase voltage. VNY, this is what? This is the potential difference between these line y and this neutral point n. Okay, this is also line to neutral voltage or the phase voltage. Okay, and what is the phase difference between each of them? It is 120 degree. They are 120 degree out of phase from each other. So how can we represent this one? So my VNR, VNB, VNY, they are my line to neutral voltage or phase voltage. And these VR, VY and VB, these are my line to line voltage or line to line voltage, whatever you call it. So can we write this as it is? If we represent it in terms of vector, so this is VNR, VNY, this VNB. These are my all three black color arrow that you are observing, that are my line to neutral voltage or phase voltage. So what is the phase difference between them? This is 120 degree, this is 120 degree, this is 120 degree. Now if you rotate anti-clockwise, because we have already seen in our previous lecture how to represent a phasor. Okay, now the potential difference between these R and Y is VYR. Okay, that is my line voltage. The potential difference between these VR and R and V is VRV. Okay, and the potential difference between B and Y is VBY. Okay, this is the vector representation of the phase voltage. Okay, so here it is shown the star connection of the phase winding. These all are my phase voltages, and these are VR, VY, VB. These are my line voltage. Okay, so this is a 3-phase and 4-wire system. Three phase lines we have, 3 phase wires we have, along with that neutral wire we have in the star connection. That is why it is called a 3-phase 4-wire system. Okay, next, if we consider these mod of VR, mod of VY, mod of VB, these are my line to line voltage that we have already seen in previous slide, or line voltage. If we consider them as V phase, then what will happen? That means we are considering line voltage equals to phase voltage. Okay, now if I draw because if I draw the line voltage is what? This is my line to, this is my what voltage? VRY, this is my line voltage. VBR, this is also my line voltage. VYB, this is also my line voltage. Okay, now how to find the expression of the line voltage in case of the star connection? So VRY, that means I want to find out the voltage between the line R and line Y. Okay, that is my VRY. Okay, so VRY means what will happen? It is the vector difference between, can we write VRY equals to VR minus VY. Now if we represent it in terms of vector, how it will look like? This is my VR, because we have already represented it, no? VR equals to V angle 0, VY equals to V angle minus 120, VB equals to V angle 120. That means each of these VR, VY and VB should be 120 degree apart from each other. The phase difference between each one of them should be 120 degree. So VRY can, so this is VR, VY and VB. Okay, so if this side is VY, if we extend it opposite side, it will be minus VY. Okay, so this is my VR, this is my minus VY. So this will be my resultant vector VRY of this VR and minus VI component. Now this is 120, this is 120, again this is 120. If this entire thing is 120, then this is my 60, and half of that, this is my 30. Okay, that means the angle between VR and minus VY is 60, but the angle between this resultant VRY and minus VY is 30. So if we, as per the vector geometry, we know VRY will be root over of VR square plus VY square plus 2 VR VY into cos 60. Okay. Now, cos 60 is what? This 60 degree is the angle between these VR and these minus VY. Okay. So, we have already considered this VR, VY, VB. This line voltage equals to phase voltage. So, instead of this, in place of VR, VY, we can easily put V phase. So, what we will get? This VRY, which is my line voltage, equals to root 3 of V phase. So, this is one relation we got between the line voltage and phase voltage in case of the star connection. Okay. Now, we have already seen many times VRY, VYB, VBR. These are nothing but my line voltage, the voltage difference between two line. Okay. So, previous slide we just have received this VRY line voltage equals to root 3 V phase. Okay. Now, we also have seen that each line is in series with its individual phase winding. Here, each line is in series with the individual phase winding. Okay. So, in star connection, the line current in each line is the same as the phase winding to which the line is connected. Okay. Since each line is in series with the individual phase winding, so in star connection, line current equals to phase current. That means IL equals to root 3 I phase. Okay. Sorry, IL equals to I phase in case of the star connection, but VL equals to root 3 V phase. So these two are very important connections in two important formulas in case of your star connection. Okay. And any balanced star network we have already seen, if we are connecting the equal loads, then the sum of the current flowing at any instant of time through the neutral conductor is 0. Okay. So, how we will calculate the power in case of star network? Okay. So, this is a three-phase system, right? So, what is the total active power? We have seen already how to calculate the active power, and it is the power consumed by the resistive component only. So, it is individual phase power is V phase, I phase, cos phi. Okay, that is the active power formula, right? VI cos phi. So, since we have the three phase, so it will be multiplied by 3. So, these 3 we can write it root 3 multiplied by root 3 and then V phase, I phase, cos phi. So, root 3 multiplied by this root 3 V phase is nothing but the VL. So, we can write VL, and I phase is nothing but the IL in case of star network into cos phi. And then if it is in, we know active power is either in watt or kilowatt. So, multiplied by, we can write 10 to the power minus 3 kilowatt. And reactive power is the VI sin phi component. So, it will be root 3 VL IL sin phi multiplied by 10 Q kVAR. We know it is in kilovolt ampere reactive, and total apparent power is nothing but the vector sum of these active power and the reactive power is equals to root 3 P square plus Q square. So, it is root 3 VL IL volt ampere. Okay. Now, we will see another three-phase system which is called the delta network, since it looks like the Greek letter delta. Okay. Now, each of these current IRY, IYB, IBR you are observing here, these are my phase currents. Okay. And these IR, IY, IB, these are my line currents in case of the delta network. So, if I want to find the line current, what will be my formula? I have to, suppose I want to find the line current IR. So, at this point I will apply the KCL. So, in this point, what are my incoming current and outgoing current? this IBR is my incoming current and this IRY and IR my outgoing currents. So if you apply KCL at this point, you will get IBR equals to IRY plus IR. So from here we can write IR equals to IBR minus IRY. Similarly, if you want to find the current, line current IY at this point, then what can we write? IRY equals to IYB plus IY. Okay, from here you will get IY equals to IRY minus IYB. Similarly, if you want to apply KCL here to find the line current IB, so it will be IYB equals to IBR plus IB. So it will be IB equals to IYB minus IBR. Just the vectorial difference, okay, between the phase currents if we want to find out the line current. Okay, so if I want to represent each of these line current in terms of the vector, so how we will represent? If I want to represent each of these line currents, how we will represent? Better represent the phase currents IRY, IYB and IBR, because we know they are 120 degree out of phase from each other. So this is my IRY, this is my IYB and this is my IBR. Okay, and the phase difference between IRY and IYB is 120, then IRY and IBR is 120, again IBR and IYB is 120. Okay, now this component is my IBR, right? This component is my IBR. If we extend it in the opposite side, it will be minus IBR. So this component is IRY, this component is minus IBR. So obviously their resultant will be IR as per this vectorial difference. Okay, so this angle, this total angle between IRY and minus IBR is 60. So the angle between this resultant line current IR and this phase current minus IBR will be 30 degree. Okay, so IR we can write it is IBR minus IRY. So how can we represent in terms of vector? Root over of IB square plus IR square plus 2BR to IBR into IRY into cos 60, because the angle between these two phase current IRY and minus IBR is 60. So if we assume that all these phase currents they are equals to this I phase, okay, then what can we write? All these are phase currents, right, equals to I phase. Then in place of IBR, IRY, we can simply write I phase. So it will be IR will be equals to root 3 I phase. This IR is nothing but the line current. So here we got a relation between the line current and the phase current in case of the delta network. Okay. Now, but since in star network we need a neutral and two separate voltages, but in delta network we don't need any neutral wire, and because in delta connection it is mainly used for high voltage systems. Okay, now if we consider, so since in delta network we don't have any neutral, so phase voltage is equal to the line voltage. So each of these VRY, VYB, VBR, each of these voltages is considered equals to the VL, line voltage equals to phase voltage. So in case of a delta network, VL equals to V phase, but IL equals to root 3 I phase, just opposite to your star. In star connection, we have IL equals to I phase, but VL equals to root 3 V phase. Okay. Now, how to calculate the power in delta connection? Same. Active power is V phase I phase cos phi in a single phase. So, 3-phase system total active power will be multiplied by 3. Now, in delta connection, V phase equals to VL and This one we have seen IL equals to root 3 I phase. So I phase will be IL by root 3. So what will be my total active power? This we got, no, 3 into V phase I phase cos phi. So if we want to represent in terms of line voltage and line current, what we will do, this 3 we can write root 3 into root 3. V phase means V phase, VPH means V phase is V line voltage, and I phase we can write as it is multiplied by cos phi. So this will be root 3 VL into root 3 I phase means IL cos phi. So this is in watt. If I want to represent it in kilowatt, will be multiplied by 10 to the power minus 3. So this is root 3 VL IL cos phi is my active power, total active power in the three phase system. So what will be my total reactive power? It will be the sine component. So it is represented by Q equals to root 3 VLIL sine phi. Unit is volt ampere reactive. So if you want to represent it in terms of kVAR, so multiplied by 10 to the power minus 3. And we know the apparent power is a vector sum of these active power and this reactive power. So it is root over of P square plus Q square. That means root over of 3 VLIL volt ampere or root 3 VLIL 10 to the power minus 3 kilovolt ampere.